Here's another example involving first order circuits where we have a couple of sources, a couple of voltage sources, along with this 10 microfarad capacitor, which initially has no stored energy since its initial voltage is 0, and a 10K resistor. So before the switch is closed at t equal to 0, there's no current flowing in this circuit, but then once the switch is closed, it connects the circuit together. So now, well, it connects both halves of the circuits together. So now current's going to flow and this capacitor is going to charge as time progresses. So these are our two curves that we want to find the start points, the end points, along with how much time in between. Okay, so the initial voltage and current along with the steady state voltage and current along with the 5 time constants in between. So to start off, we're going to analyze the t equals 0 plus circuit. So we replace the initially uncharged capacitor with the short, and if I find the voltage across that short, well, that's going to be the same as the voltage across the capacitor at t equals 0 plus. And the voltage across the short, as we've seen many times, is 0 volts. And then if I find the current for the short, well, that's the current for the capacitor at t equals 0 plus. So you can see here, current's going to flow in this direction from the plus 24 volts to the 18 volts. And in that single path, there's just this one 10K ohm resistor. So the difference in voltage across that 10K is just the difference of the two sources. So we're going to have 24 minus 18 divided by 10K. So that gives us a current of 0.6 milliamps. Okay, so going back to our curves, we found that this voltage curve for the capacitor starts at 0, and this current right here, the initial current, capacitor current, is 0.6 milliamps. Alright, so now let's find the steady state values. And to do that, we have our steady state circuit where we replace the initially uncharged capacitor with an open. So to find the voltage across the open, we just need to find the voltage on each side of the open, okay, these two nodes here, and then take the difference. Okay, so I'll label this node A and this B. So VB is just going to be equal to the 18 volt source, since this node is on the plus side of this 18 volt source and the other side's ground. So that's just 18 volts. Oops. 18. Let's draw that over again. Okay, so yeah, 18 volts. It's a little bit better. So that's VB. Now we know this node here has 24 volts, and then in between this node and node A is this 10K ohm resistor, but because the current is 0, since we don't have a complete path, the voltage across this 10K ohm resistor is 0. And anytime you have 0 volts across something, just like when you have 0 volts across a short, it means the voltage is the same on both sides. So VA is just going to be 24 volts. So the voltage across the open okay, which is equal to the voltage across the capacitor at steady state, is just going to be the difference, 6 volts. Difference of 24 volts and 18 volts, so 6 volts. And then a current for an open, okay, which is the same as the current for the capacitor at steady state, is just going to be 0. Okay, so we can go back to our voltage and current curve, and write in that this VC here is 6 volts, steady state, 6 volts, right? That's what the capacitor is going to charge up to. And then the steady state current is going to be 0 for all practical purposes. Okay, so now we just need the time in between t equals 0 and steady state, which is 5 time constants. So this circuit only has one resistor, so we don't have to find an REQ here. R is just, whoops, you go back a page. See, we don't have REQ here because we just have a single 10k ohm resistor. So our time constant is just going to be tau equal to 10k for the resistance. And then the capacitance in this problem was 10 microfarad. So that's going to give us a tau of 500 milliseconds, okay, which is half a second. And then 5 taus would equal 5 taus would be or actually I made a mistake here. I'm sorry, I was looking at my notes and not paying attention. This is 100 milliseconds, right? Because 10 times 10 is 100, and then k plus 3 times mu, which is 10 to the minus 6, gives you milli. So then 5 taus is half a second, or 500 milliseconds. Okay, that's our 5 tau. So to complete our curves, we just need to show that the amount of time from t equals 0, okay, for both the voltage and the current, right, it's going to be half a second. Okay, 500 milliseconds, which is the same thing as half a second. All right. Now, here's an additional problem. Okay, this problem right here, where we have a capacitor that before t equals 0 has been charged to a voltage of 6 volts. So here's a capacitor that has initial stored energy. Okay, since there's an initial voltage across its plates, it's storing energy initially. And at t equals 0, we're going to connect up this initially charged capacitor to some resistors, okay, the 8K and 16K in parallel. So it should make sense that since this capacitor has stored energy to begin with, and since we're connecting it to a circuit that only has resistance, well, this is a discharging case. So both the voltage across the capacitor and the current for the capacitor are going to be decaying exponentially. So to find where these curves start, where they end up, and how long in between, we're going to start with the t equals 0 analysis, t equals 0 plus analysis, where we find what the initial voltage or the voltage across the capacitor at t equals 0 is, and what the capacitor current is at t equals 0. So to do that, we look at the t equals 0 plus circuit, and here the capacitor is represented with a voltage source of the same value as what the initial voltage is, which in this case is 6 volts. And you know, this is based on the characteristic of a capacitor that it's going to have the same voltage across its plates just after a switch changes, the same as the voltage it has just before the switch changes. So whatever voltage a capacitor has before a switch changes, it's going to have the same voltage the moment right after the switch changes. Okay, so we represent the initially charged capacitor in this case with 6 volts because that's its initial voltage. So now if I find the voltage for that 6 volt source, well, that is the voltage across the capacitor at t equals 0 plus, and if I find the current for that 6 volt source, well, that's the current for the capacitor at t equals 0 plus. Well, this one's easy, right? Because the voltage across a 6 volt source is 6 volts. Okay, and then here, to find the current for this source, we just need to find the REQ, or at least one way to do this problem is we could find the REQ for the resistors here that are in parallel, and then divide that into our 6 volts. So REQ is 8K in parallel at 16K. So if you do product over sum, you'll get that the REQ is 5 1/3 K. And then the current for the 6 volt source is just 6 volts divided by 5 1/3 K. And if you work that out, that comes out to 1.125 milliamps. Okay, so now if we look at our curves, this decaying exponential for the voltage starts at 6 volts. Okay, and this starts at 1.125 milliamps. Okay, now to get where these curves end up, we just use some of our circuit knowledge that since the discharge path, okay, once this switch closes and it connects this initially charged capacitor to this discharge path, well, since the discharge path only has resistance, given enough time, namely 5 time constants, all this stored energy is going to be dissipated as heat by these resistors. So there's really no steady state analysis to do in this particular case. It's just that we understand that all the stored energy is going to be dissipated in the resistances given enough time, 5 time constants, and therefore the stored energy of that capacitor will be depleted by that resistance, and both the voltage at steady state and the current at steady state are going to be 0 in this discharge case. Now, if you have another source along with resistances in the discharge path, then there's going to be something different, and a little bit more of an analysis we'll have to do. And actually the next video will have an example involving a source in the discharge path, so we'll get to that in the next video. Okay, the last thing here is getting the amount of time that it takes to discharge between t equals 0 and steady state, and that involves tau, which is REQ, since we have more than one resistor this time, times the capacitance. So we already found the REQ in the previous analysis to get the current, right? We found that that was 5 1/3 K, and then the capacitor is 10 microfarads. Okay, and then remember, it's going to be 5 taus. So 5 times 5 1/3 K times 10 microfarads comes out to a total of 267 microseconds. Okay, so again, that's micro. Sorry for the messy writing here. Okay, so microseconds. Alright, so that's the time from t equal to 0 out to the time steady state where both the voltage and current become 0. That's our 5 taus. Alright, so that completes this video, and the next video will have a problem where we have a voltage source in the discharge path along with some resistance.